Back in 2017, some researchers at Google dropped a paper with this kind of simple, kind of bold title, "Attention is all you need." And let me tell you, this paper wasn't just some small update. Nope. It was the blueprint for pretty much every major AI thing we've seen since. We're talking everything from language translation to the very models that power tools like ChatGPT. So what was the big revolutionary idea hiding inside?
All right, so here's how we're going to break this down. First, we'll look at the big problem that old AI models were stuck on. Then we'll get into the breakthrough idea that just blew it all open. After that, we'll check out the brand new architecture they built, peek under the hood to see how it works, and finally, we'll look at the results. And trust me, they were game-changing.
So before 2017, if you were working with language AI, you were probably using something called a recurrent neural network, or an RNN. These things were the kings of the hill, the best we had. But they had this one major, fundamental flaw that was holding everything back.
Okay, imagine you're reading a book, but you can only read one word at a time. And you can't move on to the next word until you've completely 100% understood the word you're on. Sounds slow, right? Well, that's exactly how RNNs worked. And this one word at a time thing was a huge bottleneck. You couldn't speed it up by having different parts of your computer work on the sentence at once. And, even worse, it made it super hard for the model to remember a connection between a word way back at the start of a paragraph and another one at the very end.
This slide right here, it just lays out the problem and the solution so perfectly, and this is data straight from the paper. On the left, you've got the old way, the recurrent layers. See how the number of steps the computer has to take just keeps climbing with every word you add? It's a straight line up. But then, look to the right. That's self-attention. It doesn't matter if the sentence is 5 words long or 500, it's just one step flat. This wasn't just a small improvement, you guys. This was a complete and total paradigm shift.
So what was this magic bullet? What was this incredible idea that made all this possible? Well, it was a mechanism that had actually been around for a while, but it was always kind of in the background, a supporting actor, never the main star. And that concept was called attention.
Yeah, the definition from the paper sounds a little dense, but the core idea is actually super intuitive. Think about this sentence. The robot picked up the ball because it was heavy. Now, what does it refer to? The robot? The ball? For you to understand that sentence, your brain has to pay attention to the other words. Self-attention gives an AI model that exact same superpower. For any word it's looking at, it can scan the entire rest of the sentence and figure out which other words are the most important for getting the context right.
And right there, that was the paper's most radical, most out there proposal. The authors basically said, hey, you know that slow, one word at a time thing? Let's just get rid of it completely. What if we build a brand new model from the ground up that runs entirely on this self-attention concept? I mean, it was a really bold, almost crazy idea at the time.
And the new architecture they created, this new blueprint built purely on attention, well, they gave it a pretty fitting name, the Transformer.
And this is it. This is the official diagram from the paper, and honestly, it's become one of the most famous pictures in all of modern computer science. I know, it looks a little intimidating, but it's really just two big parts. Over on the left, you've got the encoder. Its job is to read and really understand the input sentence, let's say a sentence in English. Then on the right, you have the decoder, which takes that understanding and uses it to generate the output, like translating that sentence into German.
So if you were to zoom in on that encoder and decoder, what would you find? Well, they're basically just a stack of 6 identical layers, one on top of the other. And each of those layers is surprisingly simple. It really only has 2 main components. First, you have that multi-head self-attention thing we've been talking about, and second, just a regular old neural network to do a bit more processing. That's pretty much it. Simple, super elegant, and as we're about to see, incredibly powerful.
Okay, so we keep saying attention is the secret sauce here. But what does that actually mean? How does it work? Let's pop the hood and take a look inside the machine to see how these things actually learn to see the connections in our language.
All right, I know this looks a bit scary, but stick with me. The core idea is actually pretty simple. On the left, that's the basic attention calculation. That's the engine that lets one word figure out how important all the other words are to it. But here's where the real genius kicks in. Instead of just doing that once, the Transformer runs 8 of these attention engines at the exact same time, in parallel. They called this multi-head attention. And trust me, it's a total game changer.
So why on earth would you run 8 of these at once? Well, think of it like having a panel of 8 different experts all looking at the same sentence. One expert might be really good at spotting grammar.
Another might focus on the action, like who did what to whom. A third expert could be looking for more abstract, conceptual links. Multi-head attention lets the model look at the sentence from all these different points of view at the same time, which gives it a much richer and more nuanced understanding of the text.
Okay, but this brings up a huge question, right? If we've totally ditched the old one word at a time method and the model is just looking at all the words at once, how in the world does it know the difference between the dog bit the man and the man bit the dog? I mean, the words are identical, but the meaning is completely different.
The solution they came up with is it's so clever. Before the words even go into the model, they add a special mathematical signal to each one. It's called a positional encoding, and it's made using sine and cosine waves. Now, you can basically think of this as adding a tiny invisible timestamp to every single word. It tells the model, hey, this word was in position 1, this one was in position 2, and so on. And just like that, the model gets back all that crucial information about word order that it seemed to have lost. So there we have it, this new, elegant architecture. It can be run in parallel, it can handle connections between words that are far apart, and it still knows the word order. But the million-dollar question is, did it actually work? Well, the results they published weren't just a small step forward. They were a full-blown revolution.
So they tested it on this standard, really tough machine translation task, English to German. And the transformer didn't just beat the old record. It absolutely smashed it. It got a blue score of 28.4. Now, all a blue score is a way to measure how close a machine's translation is to a professional human translation. And in that world, improving by even a fraction of a point is a big deal. Improving by over 2 full points, that's a seismic event.
But here's the real kicker. Because of that parallel design we talked about, it got that record-breaking score while being way cheaper and faster to train. The big model only took 3.5 days on 8 GPUs. And look, this isn't just about saving a company some money. When you make training this much faster and cheaper, you open the door for researchers everywhere to start building much bigger models. It completely democratized high-end AI research and paved the way for the giants we have today.
And it wasn't a fluke. On the English to French translation task, it was the exact same story. This table from the paper really tells you everything you need to know. The transformer gets a new state-of-the-art score, beating out all these other complex models. But look at that last column. The relative training cost is listed as low. The conclusion was just undeniable. It was better, it was faster, and it was cheaper. In the world of computing, that's the holy grail, and that's what truly changed the game.
So in the end, the paper proved its point and then some. It showed without a doubt that you could build a world-class AI model without all that slow, sequential processing, relying only on this idea of attention. And that discovery didn't just make machine translation better, it totally changed the direction of AI research. It unlocked the parallel power we needed to create the massive large language models that are, well, they're everywhere today. The paper's title was such a bold claim. Attention is all you need. And I guess the question it leaves us with is, now that we have it, what will we build with it next?